Hello everyone. So before starting, can I get a thumbs up if I am audible, if my mic is working properly?
Yes, sir. You are audible.
Thank you. Okay, I'll wait for maybe 2 minutes. So if others want to join, they can join and then we'll start. In the meantime, if anyone has anything to ask, feel free to unmute yourself and ask. All right, I guess no one else is joining. Anyway, that is not a problem. So I guess we can start. So let me first give a brief intro about myself. My name is Manav Beniwal. I am doing my PhD in Indian Institute of Science, Bangalore, in the Department of Physics, and I have been assigned as a PMRF TA for this course, Atomic and Molecular Physics. And I'll be taking tutorials every week on Saturday. And in these tutorials, for 2 hours, we will be mostly solving problems which are related to the content of the course in the respective week. So for this week, professor has taught us regarding the different experiments which led to the discovery of parts of an atom. For example, there was Michelson's experiment, there was the famous oil drop experiment, and so on. So I hope everyone is familiar with them. And to make the best use out of these sessions, I encourage you to stop me at any point when I am discussing solutions and clarify things how much ever you want. Okay? Any questions before we begin? If not, then we can start solving problems right away. Also note that these problems will be somewhat similar to the problems which you guys have been asked to do in your assignments, but they will not be the same problems. And as part of the policy, I cannot discuss the assignment problems until the assignment deadline is over. Once the assignment deadline is over, then you can feel free to discuss the assignments if you guys had any difficulty. Okay. So as other peoples are joining in, I guess we can start our session. In the meantime, I'll write the problem and then we can start solving together. So let's begin by first question. And the question is the quantity of electricity required to liberate 0.2 gram equivalent of an element at the electrode is, and you have four options. Okay, so the question states that we are required to find out the quantity of electricity. So what do we need to find? Quantity of electricity. For what purpose? That it has to liberate 0.2 gram equivalent of an element. So 0.2 gram equivalent of an element at the electrode. Okay. So as discussed in the class, we know about 1 Faraday. What is 1 Faraday? 1 Faraday, which is written as F, its value is 96500 coulomb, roughly. Okay. This is required for 1 gram equivalent of an element. Okay, correct. So if we have any element, okay, we have any element and we want to deposit it on electrode. So to deposit 1 gram equivalent, we need 1 Faraday of charge, right? So then 1 gram requires 1 Faraday. So 0.2 gram equivalent will require 0.2 Faraday, which is nothing but 0.2 multiplied by 96500. And therefore, the answer will be option D. Is this clear? If no, feel free to unmute yourself and ask what part you did not understand. Otherwise, we'll move on to the next problem. This was a fairly straightforward problem. It just requires us to know what 1 Faraday of charge means, right? So 1 Faraday of charge means this is the amount of charge which will deposit 1 gram equivalent of an element on the electrode. So for 1 gram, we required 1 Faraday. Therefore, for 0.2 grams, we'll require 0.2 Faraday. And by simple multiplication, we get our answer. Okay. If you are hesitant to open your mic and speak, you can also type your doubts in the chat box. That also works. I'll keep looking at the chat box at regular intervals. Okay. Let's go for second question. During the electrolysis of molten NaCl, which is sodium chloride, the time required to produce 0.25 mole of chlorine using a current of 5 amperes is okay. So let us understand the problem. What does the problem ask? It asks us to calculate the time required. Okay, so we want to calculate what is the time required to produce 0.25 mole of chlorine, and the current given to us is 5 amperes, right? So we have a solution of NaCl here, right? So this is our NaCl, and here we have two electrodes, and then let's say this is the positive electrode. So the chlorine gas will be, because chlorine is what, Cl minus, so chlorine gas will be released here, correct? Now how much time it will take so that 0.25 mole of chlorine gas is released? I hope the question is clear, right? So let us write it systematically. Let us write mass of chlorine gas. Let's say this is m. M will be number of moles multiplied by molecular weight, right? Correct. So we are given the gas in terms of moles, right? 0.25 moles. So we'll write 0.25. And what is the molecular weight of chlorine? Because it is written chlorine gas, so chlorine gas will be Cl2 and molecular weight will be 71 grams. Okay, so we multiply by 71 and this comes out to be 17.75 grams. Now let us write the equivalent weight of chlorine. So the equivalent weight of chlorine, that will be, let's say we denote this by mu. So this will be 35.5 grams. Why? Because the valency of Cl in NaCl is 1. Correct? So the equivalent weight of chlorine will be 35.5 grams. And now we know everything, right? So now the time can be written as the equivalent weight m multiplied by our constant Farad divided by our equivalent weight and multiplied by current. Okay. So if this formula seems little unfamiliar, this is just what do you say? Just another way of writing the formula which was discussed in the lectures. So in the lectures, we wrote the mass deposited is Q times mu by F upon nu. So this was valency, right? And this F is F and this Q. So now I have just substituted the charge as current multiplied by time, right? So if I put this in this equation, then I get this formula for time. Yes? Okay. And here valency is simply 1 in this case for chlorine, right? Now we can plug in the values. So our T will become 17.75 multiplied by 96500 divided by 35.5, and current given to us was 5 amperes. Okay, the current was 5 amperes, so just multiply by 5. And if we solve this, so we get 9650. Okay. Okay, because this will just give 1 and this will give 2 and this will give 10 and then this will give 9650. So the correct option will be option B, 9650 seconds. So this problem gives us an idea, like 0.2 gram of chlorine is not very huge amount of gas, right? It is comparatively just a normal amount of gas. And if we use a normal current of, let's say, 5 ampere, which is not very high current and not a very low current, so to if you want to remove, let's say, if you want to produce only 0.25 moles of chlorine, this will take around this much seconds. And if you convert this to hours, let me just do this. So this is roughly 2.7 hours. Okay. So just producing 0.25 moles of chlorine in an electrolysis will take around 3 hours. So just to get an idea of how long does it take to get this much amount of chlorine or any other element for that matter. Okay. Any doubts in this question?
No, sir.
Okay. Thanks for confirming. Okay. So let us solve one more. And this time I want you guys to tell me the solution before I begin solving. It is very similar to the problem we just did. Okay, so I'll just write it out. Try solving, and I would really like to know the answer before I solve. You can type your answer in your chat box. That will be great. So the question is, how much aluminium, which is Al, right, would be precipitated in AlCl3 solution if electrolyzed for 965 seconds. with the current of 10 amperes. Okay, very similar problem. Just this time we have, earlier we had NaCl, this time we have AlCl3, and we are electrolyzing it for 965 seconds with a current of 10 amperes, right? And we would like to know the mass of aluminium which is getting deposited. So your options are 2.7 grams, B 3 grams, C half gram, 0.5 gram, and D 0.9 gram. Okay, I'll give you guys 1 minute. Let's see if you can solve it on your own. That will be really nice. If you guys want the formula, I'll just write it here. So the mass deposited generally is written as the charge Q divided by the constant Faraday. Then here you have mu, which is the equivalent mass when it is divided by your valency V. So this is your valency and mu is your effective mass. Okay. Oh, sorry, the equivalent mass. And I'll also provide atomic weight of aluminium. That is simply 27. Okay. Okay, let me see if anyone has any answers in the chat box. Okay. In the meantime, I'll start solving this problem. You guys can continue solving and type your answer in the chat box. Okay. So here to find out Q, we know that this is just current times your time, right? So this is 10 amperes multiplied by 965 seconds. Okay. So then our mass will be 9650. This is Q divided by F, which is 96500, multiplied by mu is 27 and nu is 3. Because here in AlCl3, aluminum is in plus 3 state, right? So this is plus 3, chlorine is minus 1, and we have 3 to balance out the charge. Correct? So this simply gives us 1, 10, 1, 9. So this is nothing but 9 over 10 or 0.9. So the answer will be D. Okay. Yes, correct. Ellen John Sony with the correct answer. Okay, I hope this thing is clear by now, right? Okay, yes. Thanks for confirming. Yeah, if anyone is having any trouble, just type in the chat box. I'll explain everything later. Okay? I hope this should be okay. Great. Let's do another one. Again, this is an MCQ. I would encourage you to solve along and let's see if you get the correct answer. Okay, this one is little next level. Okay, now we are moving to little more difficult problems. Okay, so the mass of a substance, we don't know the substance, just a substance is given to us. The mass of substance and the mass is m. Okay, so the mass is m, deposited in electrolysis is equal to electrochemical equivalent Z. Okay, when a current is passed through the electrolysis for 5 seconds. Find the value of current. Okay, so your options are 0.4 amps, 1 amp, 2.5 amp, and 4 amp. Okay, so you can start solving, and in the meantime, I'll explain the problem. So the mass of substance deposited in electrolysis is equals to electrochemical equivalent Z. Okay, so we have two quantities that are equal. One is the mass of substance that is deposited, that is equals to the electrochemical equivalent Z. Okay, if you guys have not heard of the thing electrochemical equivalent, you might as well try to take a guess what this term can mean, right? Again, we have this formula. I'll rewrite it here. Your M is Q over F multiplied by your mu over nu, correct? And for for this problem, you will again require this formula. And here the time is given to be 5 seconds. And we want to find out current. So what is current, right? That is what we need to find out. Okay. So I'll wait for like 30 seconds maybe. Let's see if I see any answers in the chat box. Okay. So you guys carry on with solving, and I'll solve with you guys parallelly. Okay. So let's see. So the mass of substance M deposited in electrolysis is equal to your electrochemical equivalent Z when a current is passed through electrolysis. So basically, what they are what we are trying to do is your electrochemical equivalent, or I'll simply write Z. Our Z is given by M over Q. Okay, where M is the mass of substance, and this Q is the charge that has flown to deposit uh, this mass, right? Okay, so now from here we can write Q as M over Z. Also, we can write Q as current times the time, for which it flows. And how much is this T? This is 5 seconds, right? So our Q becomes 5I. Okay, so substituting this 5I in this equation, we get 5 times I is M by Z. Okay, correct. And then this would imply that your I is okay, forget, this will be 0.2, typo. Okay, option A is 0.2. Okay, and then your current is simply M by Z and times 1 by 5. Okay, now we are given that the mass of substance M and Z, they are equal, so they just cancel out, and I we get as 0.2 amperes, which is option A. Okay, okay. So the problem in this was to understand what electrochemical equivalent means. So electrochemical equivalent means mass deposited per unit charge. Okay.
Excuse me, sir.
Yes.
Sir, please repeat again. I is equal to 1 upon 5. Sir, that here.
Okay.
I'm not understood.
Fine. Okay, I'll explain it again. Okay. So the question says that we are depositing some substance. Okay. And the amount that is deposited, the mass which is deposited, that is denoted by small m. Okay. And this is equal to electrochemical equivalent Z here. Okay, and the current is passed for 5 seconds, correct? Now this electrochemical equivalent Z, which you can see here, so it is defined as the mass of substance deposited per unit charge. Okay, let's say you have an electrode here. Okay, this is your electrode, and you flow q amount of charge in it. Okay, let's say here is your some solution, and you flow q amount of charge in it. So yes, you'll get some mass deposited here, which will be m. Okay, so the mass deposited per unit charge m by q, or if this q is 1, so 1 unit of charge, the mass that it deposits, that is known as electrochemical equivalent. Okay, so then basically what the question tells us is that our mass of substance and chemical equivalent Z are same, which means m and Z are same in this equation. In this equation, m and Z are same. What will that mean? This will simply mean that the charge you will require will be just 1 unit. Okay, you need only 1 unit of charge to deposit electrochemical equivalent of a substance, right? So now once you have q is equals to 1 and you have time as 5 seconds, you have time as 5 seconds, so you can simply calculate your current as I is q by t. Correct? So that is what we have done here. Could I explain or should I repeat it again? Here in this equation where you are asking me here, basically the mass deposited and the chemical equivalent both are same. So they just cancel out and we are left with 1 over 5. Right? So our current is 0.2 amperes.
Thank you, sir.
Okay. Thank you. So okay, enough of electrolysis. Let's do. Sir, can you explain electrochemical equivalent? Yeah, sure. So, okay, let's first finish with this electrochemical equivalent. This is denoted by Z generally. Just one second. Okay. So what I said was that it has this formula, mass over charge, right? And this charge can be any number. Let's say here we have same figure. We have a solution. We have one of the electrodes here, okay, the other electrode here, and we pass some charge q through them, right? Some charge q is flowing in this thing. Okay, how will this charge q flow? Basically we will pass some current for some time t, and therefore you will get some total charge q, right? Q will be your current multiplied by time, right? So let's say you flow 1 ampere current for, let's say, 5 seconds. Okay, this will give you 5 coulomb of charge. Okay, and now you can take any arbitrary solution. We do not know what solution is this where we have put our electrodes. Okay, and then what you observe experimentally, that some mass, let's say 20 grams, just any random number, 20 grams of mass has been deposited in this 5 seconds, right? So we can then define property of this substance. Let's say this is some substance x. We can then define the property of this substance, which is known as electrochemical equivalent, that how much mass, okay, how much mass will be deposited by 1 coulomb of charge. Okay, So how much mass will be deposited by 1 coulomb charge? This number is nothing but electrochemical equivalent. Like for example, in this case, 5 coulombs is depositing 20 grams, right? In the example which we have taken, 5 coulombs is depositing 20 grams. So 1 coulomb, it will deposit 4 grams, right? So then we can say that the electrochemical equivalent Z for this substance, Z for this unknown substance X, is 4. Okay. If you take some other substance, let's say Y, it will have some different Z. It can have, let's say, Z for Y can be maybe 7. We don't know, right? Depending on the substance, how much it deposits when we pass a certain amount of charge, you get this value. Okay, I hope this is clear. Okay, so okay, let's move on. Okay, let's solve next problem. Now we'll now solve a problem for a charged particle in a electric field. Okay, I hope the electrolysis part is clear to everyone. Let us say we have a charged particle, okay, whose mass is 0.1 gram, very small particle, and charge q is 10 to the power minus 4 coulombs. Okay, a charged particle this much is thrown at an angle of 30 degree from a point A with speed 20 meters per second. Okay, consider the region to be free of gravity. Okay, somewhere in outer space, we don't know, there is no gravity acting here. Okay, however, a uniform electric field 10 volts per meter is acting downwards. Okay, calculate the maximum height h attained by the particle. Okay, I'll draw the figure. Okay, let me also give you some options. So A is 0 meters, B is 5 meters, C is 10 meters, and D is 12.5 meters. Okay, now let me draw the figure. So this is our point A, okay, and the particle is launched at an angle of 30 degree with a speed of 20 meters per second. Correct? And in this region everywhere we have a uniform electric field, right, which is given by E is equals to 10 volt per meter, and there is no gravity. Okay? No gravity. Is the question clear? So there is a region, okay, let us say there is a region here, and this region is free of gravity. There is a point A here from where we throw a particle which has mass m and charge q at an angle of 30 degrees with a speed of 20 meters per second. And you guys can already guess that this will go like a projectile, right? Like this. And we want to calculate what is this maximum height h. All right. Is the question clear to everyone? Okay. If no, please feel free to ask, and then we can start solving. So you can already, if you guys have solved problems related to projectile motion, which I am 100% sure you guys have done in the past. So this is a case where instead of gravity, we have an electric field which is acting downwards. Now note that the charge Q is 10 to the power minus 4 coulomb. So this is positive, right? Positive charge. And because the charge is positive, it will accelerate in the direction of electric field, right? Because the force, okay, let us do this. We know force is Q times E, and Q is 10 to the power minus 4, and this is 10 in the, okay, I'm calling this as this direction. I'm calling, okay, let us call this as our Y direction and this as our X direction. That is what we generally do, right? If this is the case, then our electric field is 10 coulomb per meter in the minus Y direction, right? So the force that we get, F is minus 10 to the power minus 3 Y cap. Okay, so we have this much amount of force on which is acting downwards on the particle. Again, we know that F is mass times acceleration, right? So this gives us acceleration is force divided by mass. And we know that the mass of our particle is 0.1 gram. Here you can see, right? So m is 0.1 gram. Now we should be careful and use SI units. So we should convert it to kg, and this will be 10 minus 4 kg. Okay. So the acceleration that we will get is minus 10 to the power minus 3 y cap divided by 10 to the power minus 4. So this is simply minus 10 meters per second square y cap direction. Okay. So we have an acceleration of 10 meters per second square, which is acting in the negative y direction. So acceleration is acting downwards. So these blue arrows, which marks the electric field, they also give us the direction of acceleration. Now we have calculated acceleration. If you happen to remember the formula for maximum height, well and good. It is given by u square sine square theta by 2a. You know u, you know theta, you know a. You can just plug in all the values, you will get 5 meters. Okay. But if you do not remember this thing, then need not worry. We can easily find out the height. Okay. So how to find out the height? We can just resolve the velocity components. So this was our point A, remember? And our velocity was here, which was having 20 meters per second, and this angle was 30, right? So we can resolve it in x component and the y component, right? So let this be Vx and this be Vy. So clearly you can see that Vx is 20 into sine 30 degrees, and Vy, no, this will be cos 30, and Vy will be 20 into sine 30 degrees, right? So this is nothing but 20 into root 3 by 2, which is 10 root 3, and this is nothing but 20 into 1 by 2, which is nothing but 10. Okay, so we have upward velocity as 10 meters per second and the rightwards velocity as 10 root 3 meters per second. Correct? And we of course have an acceleration of minus 10 meters per second square, right? So this is our acceleration. It is acting downwards. Okay. So let us find out the time when the particle starts from A and it goes up like this, and then it comes back again here. It will take some time, right? How do we find that? So the displace, if you notice, the displacement in the y direction when it comes back, that is 0. So the y displacement is equals to 0 for the entire, let's say this is point B, okay, is 0 for A to B. Okay, and now using equations of motion, we know that we can write y is equals to ut plus half at squared. Okay, and here y is 0, which is the displacement. U is simply our Vy, which is 10. T we want to find out, and acceleration is minus 10. Right? So this equation becomes 0 is equals to 10 times T plus half A is minus 10 times T squared. Right? So we can cancel out 1T. Right? So we can cancel out 1T and we can write 0 is equals to 10 minus, so this will become 2 and this will become 5 minus 5T, and this will give you T as 2 seconds. So this is the total time which it takes from going from A to B. It takes 2 seconds. If we start here, go all the way here, it is taking 2 seconds. So to calculate the maximum height when we are at this point, how much time will it take? It will take half the time, which is 1 second. Now we want to find out y after 1 second. Again, we'll use the same equation. Y is equals to ut plus half at squared, right? And we already know this u is 10 and t in this case will be just 1 plus half into minus 10 and t is simply 1. Okay, so we get y, or in this case let's write height h, and this will be 10 minus 5, which is nothing but 5 meters. Okay, which is the same as what you would have got if you just plugged in this formula. So the answer to this problem is B, 5 meters. Okay, so let me just explain again what we have done in this one. We were given some electric field E pointing downwards. Using the electric field, we we found out the acceleration. Right? What is the acceleration that our particle will feel? And once we have the acceleration, we can find out the total time that it takes to go from point A to point B. Okay, the total time that it takes to go from point A to point B. Then we divided, so we found out that this was coming out to be 2 seconds. And then if we wanted to go, if we just travel for 1 second, we would reach the maximum height. And then using the fact that if we put t is equals to 1, we get the maximum height. So this is how we solved the problem. This was a bit lengthy, so you guys take your time and ask me if you didn't understand any part of this. Okay, okay. Having done this thing, we can now move on to the Millikan's oil drop experiment, because that is where we have a charge which moves in a uniform electric field, right? Okay, so let's solve couple of problems maybe related to Millikan's oil drop experiment. So I guess this will be question number 6. I'll just check once. Yeah, so this is question number 6. It says in Millikan's experiment, negatively charged oil drop, negatively charged oil drop of mass 4.9 times 10 to the power minus 14 kg is balanced by applying a potential difference of 9.8 kV between plates of a capacitor separated by 12.8 millimeters. Find the charge on the drop and consider G to be 10 meters per second square. Okay, your options are 6.4, 1.6 times 10 to the power minus 18 coulomb and 3.2 times 10 to the power minus 16 coulomb, and D 8 into 10 to the power minus 18 coulomb. Okay, so you have a parallel plate capacitor like this. You have a small oil drop here. Okay, you know its mass, so you know its mass m, and you know that gravity is acting downwards, so the acceleration is g, and because it is balanced, so the electrostatic force will be acting in the upward direction, right? So this is the direction of your electrostatic force. Let me denote it by Fe. Okay, also notice that the particle, your oil drop, it is negatively charged. So what will be the direction of electric field? Your electric field direction will be like this, right? Because it is negatively charged, so it will move away from the electric field, correct? And gravity will try to pull it down, and therefore we can balance it. It says, right, it is balanced. So that we have to then equate two forces. So this will be mg and this will be Fe, which is nothing but the charge q times E, correct? So we can write QE is equals to mg. Now the potential is given to be 9.8 kV, and this distance d, that is given to be 12.8 mm. So then our E will be V by D, which is nothing but 9.8 into 10 to the power 3 upon 12.8 into 10 to the power minus 3. Yes, so let us then plug in the values. Our Q will be M is 4.9 into 10 to the power minus 14. G is simply 10 divided by E, which is 9.8 into 10 to the power 3, and this term will come up to give you 12.8 into 10 to the power minus 3. Okay, so this is your Q here, correct? This came by this formula. We have mg by E. Mg E is nothing but V by D. So this one, mgd by V. Here we have M, G, D, and V. Okay, so now we can solve this thing. So you can notice straight away that this term will cancel out, will give you 2, and if 2 cancel out this will give you 6.4, right? So your Q will be 6.4, and if you count the powers of 10, so this will be 10 to the power, this is minus 14 this term, plus 1 this term, minus 3 last term, and minus 3 this term. So this will be 6.4 into 10 to the power minus 19 coulombs. Option A. Okay. Any doubts in this milk and soil question? No, right? Okay. Okay. So then let me give you one problem, and please try to solve this on your own, because I really want to see if what I am doing here that is really contributing. Okay. So I'll give a very similar problem, and I would really like if you guys try to solve it, this one on your own, and then type your answers in the chat box. Okay. Okay, great. So let us begin. I'll write my problem here. So this will be question 7, and the problem is, in a Millikan's experiment, you have an oil drop of mass m is equals to 64 10 to the power minus 10 kg. Okay, heavier drop, and it carries a charge, carrying a charge 8 into 10 to the power minus 14 coulomb. Okay, a lot of charge. Now what you have to do, find the potential to keep the drop stationary. And you are given that g is 10 meters per second squared, and d, which is the separation between plates of capacitor, separation of capacitor plates, this is given to be 2 centimeters. Okay. Okay, and your options are 8000 volts, 3400 volts, 16,000 volts. Okay, so the mass m is given to be 64 into 10 to the power minus 10 kg. Your charge is given to be 8 into 10 to the power minus 14 coulomb. This is 14. Okay, and you have to find the potential to keep the drop stationary. Okay, notice that the charge in this problem is positive, so the electric field which we will be applying will be in the upward direction. So your capacitor plates will look something like this. right? And you'll have an electric field in the upward direction. So what we want to know is what is the potential difference V, so that the particle that you have here, that is stationary. So basically your mg is cancelled out by your qe, right? Okay, I'll wait for a minute, right? I really appreciate if you guys text your answers in the chat box. Okay, so in the meantime that you guys solve it, let me also solve in parallel. So as I said, we only have to equate these two forces, QE and mg, right? So let me write mg is equals to QE. This will give me E as mg over q, and m is 64 into 10 to the power minus 10, g is 10, and our q is 8 into 10 to the power minus 14. Okay? So this 8 will cancel out to give us 8 here, and this 10 to the power minus 14 will go up. This will become 10 to the power plus 14 and cancel out this, and we'll get 10 to the power 5. Correct? Okay. So basically we get E as 8 into 10 to the power 5. Okay, now we know that our electric field is given by V over D. So this means our V is simply E times D, and D is equals to 2 centimeters, and writing in terms of meters, our D is 0.02 meters. Okay, so this would imply V is 8 into 10 to the power 5 multiplied by 0.02, which is nothing but 16,000 volts. Yes. So the correct answer is D, as pointed correctly by Alan. Okay. So I'll pause for a minute. I would like to ask if anyone has any doubts here in the two problems that we just discussed related to the Millikan's experiment. Yes? No?
No, sir.
Okay. Great. So let me draw one current versus time graph. Let's say this is your current axis, this is your current, okay, and this is your time, time, and the dimensions for this is seconds, and for currents is ampere. Okay, let's say you have a current that flows like this. It goes here, then it goes here, maybe not this much is fine, and then it goes here. So this is how your current is flowing in the system. So this value, this is 1 ampere, and this value, oops, this is 2 amperes. This time, this is 10 seconds. This time is 20 seconds, and this time is 30 seconds. Okay, so now let me write the question. So the question is that, as shown in the figure, current flows in the current as shown in the figure, see figure, flows in electrolysis experiment. If mass deposited after 30 seconds is m, okay, then the electrochemical equivalent, then the electrochemical equivalent, electrochemical equivalent, remember we denoted this by Z, and the electrochemical equivalent Z of this substance is numerically equal to, and here again you have 4 options: m, option B is m by 3, option C is m by 30, and option D is m by 4. Okay, do you understand the problem? So we have a substance, and then the current is flowing as shown in this figure. Okay, you can see in this figure the current first increases for 10 seconds from 0 to 1 ampere, then it stays constant for another 10 seconds, and then it again increases from 1 ampere to 2 ampere in the next 10 seconds. So there are basically 3 regions, right? This is region 1, this is region 2, and this is region 3. And after 30 seconds, after all this current has flown, we get m amount of mass deposited in our system. Okay, so we get the amount of mass m that gets deposited after 30 seconds. Now what we want to find out chemical equivalent of this substance. Okay, how did we define chemical equivalent? Do you remember? Chemical equivalent is nothing but mass per unit charge. So Z is equals to m over q. Okay. If q amount of charge flows and it deposits mass m, then m over q gives us the electrochemical equivalent of the substance. Correct? Now here the mass is given m, and what we need to find out is the value of this q. We do not know what this q is. So from this figure, right, we see this figure here. From this figure, can we calculate q? We have current and we have time. Can we find out q? What do you think? Yes? Yes. Right. Now, how to calculate? So, for example, when let's consider region 2. Okay. I'll start with region 2. Okay. So, for region 2, there's a constant current flowing, right? You can note that between 10 seconds and 20 seconds, the current is constant and it always has magnitude of 1 ampere, right? So the charge in this region 2, let me write it as Q2. This will simply be current multiplied by time, which is nothing but 1 multiplied by 10 seconds, which gives you 10 coulomb, right? But what about region 1 and region 3, where the charge is not constant? Here, what value of I will you take, right? So for this problem, what we do is, this is similar to the problem where we calculate area under the curve, right? We say that the area under the position time curve gives us the velocity. Similarly, area under the current time curve gives us the charge. Why? Because you can see that your current I, okay, the current I is defined as dq over dt. So your current dq you can write as I dt, and then your charge q you can write as integral of I dt from time t1 to time t2. Yes, and integration is nothing but calculating, this is nothing but the area under the curve, right? This is area under the curve. So what we really want to do is, we want to find out the total area. Okay, let me find the highlighter and let me change the color to red. Okay, we would like to find out this area. This will give us the current in region 1, and if we find out this area, this will give us the current in region 3. Yes, and for region 2 we have already calculated, but we can again calculate and find out the basically what is the area under region 2. Okay, so let's find out. So for region 1, okay, for region 1 I'll write here. So area, sorry, my bad. So area of region 1. Okay. So because this is a right angle triangle, right? This is a triangle. So it is just half into base into height. So this will be half. Your base is 10 and your height is 1. So this is nothing but 5. Yes. Area 2 is simply a rectangle. Your length is 10 from here to here. It is 10. And your height is 1. So this is 10. And for 3, you can divide it in two parts. One is the triangular part here, and another is this squared part, right? So basically what you will get is area of 3. This will be 10 into 1 plus half into 10 into 1. So this will be 15. Right now, if you add all three area 5, 10, and 15, your total charge Q will come out to be 30. Right? Your total charge is, okay, maybe I should write 30 coulombs. Correct? So now here, coming back here, now we know our Q, right? So our Q is now 30. So we can write Z as M over 30. And our answer is C. Any doubts in this one? Anyone? Okay. Is this thing clear that how we calculate charge from a current versus time plot? Because charge is defined like this, right? This simply means that we can find out the area under the curve. If you wish, you can even find out charge by integrating. You can write the functional form of your current I as a function of time t, right? And then integrate in all three regions, and you will get your total charge Q. Okay. Do you guys want me to show you how to calculate the charge by integration in this case? If not, then we can move to the next question. If you guys are comfortable with this, please tell me. We can proceed further. Otherwise, I can explain it once again. Okay. What was this question number? This was question 8. Okay. Let's do question 9. Now, this question is related to Thomson's experiment. And this question I have taken from the book Branston and Georgian, which is also the textbook for this course. So this is the problem 1 of chapter 1, and it goes like this. Consider a Thomson apparatus with following dimensions. Now what are the dimensions? Your length of condenser plate, x1 is equals to 0.1 meters. Distance from plate to screen, x2 is 0.45 meters. Distance between the plates, that is d, is 0.03 meters. Voltage applied V is 1500 volts. Okay. Okay. Now the question is a deflection on the screen this is your y2 is observed to be 0.2 meters. Okay. This deflection is reduced to 0 if a magnetic field B is equals to 1.1 into 10 to the power minus 3 Tesla is applied. Okay. Now this has two parts. First part is find the velocity V of the electrons, and second part is find the value of E by M. Okay, so this is the problem. Pretty lengthy problem. So let me first draw diagram of this Thomson apparatus. I'm sure you guys have attended the lectures and the professor has discussed about this experiment, and the notations written here are exactly the same as were discussed in the lectures. Okay, anyway, I'll draw this condenser plates here. So one plate is like this. My bad. Other plate is like this. So this distance is x1. Okay, and you have your screen here. This is your screen. This distance is x2. Okay, let me draw it again. Okay, this is x2 and this is x1. This is d. This distance is d, and then you have your electrons coming like this. Okay, and when you apply electric field, right, that is when you apply a potential V here on these plates. Okay, so then you get an electric field. So then your these particles they get deflected, right? So then they get deflected like this. Maybe I can just draw a straight line. Sorry. Okay, like this, right? And then this distance, this small distance, this deviation, this is known as y1, and this big deviation, this is known as y2. Correct? This was what was being discussed in the class, right? Now, what other thing is discussed, that when you apply field B here, then your electrons, then the deflection is zero. So basically, your y2 is zero in magnetic field B. Yeah. Okay. Now you can see that there will be some electric field. Uh, okay, this will be, yeah, this will be plus and this will be minus. So there will be some electric field like this, and the electrons will feel this electric field, and then they'll get deflected by this distance y1, right? But when you also apply a magnetic field, then this deflection is zero, right? Which means if there is no deflection, this implies net force is zero. Now, what is the net force? Our net force F is QE plus QV cross B. Okay, and if B is applied in the Z direction to cancel out this, okay, then we can simply write, because this F is zero, we can write Q times E is equals to QVB, and this Q's will cancel out, and then what we get is E is equals to, sorry, we get E is V times B, which implies V is nothing but the electric field divided by magnetic field, E by B. Okay, and now we are given both the values, so E will be nothing but V by D multiplied by B here, and we can just plug in the values. So V is given to be 1500, D is given to be 0.03, and B is given to be 1.1 into 10 to the power minus 3 Tesla. Okay, so what do we get for V if we just solve this thing? So we get 1500 divided by 3 and this divided by 1.1. Let me just do it. We get 4.54 into 10 to the power 7 meters per second. Okay, fine. So we have solved the first part, which asked us to find the velocity v of the electrons, right? So now we can say that we know our Vx. Vx is the velocity with which the electrons are entering this capacitor, correct? Now we have the value of our Vx. This is now known to us. Okay. Now they want us to find the value of E by M. Okay. What will be the value of this E by M? Now let us find out the value of E by M. Okay. For the value of E by M, let us find out how much time it will take to cross this x1 and how much time it will take to cross this x2. Right? Similar to what we did in the class. We know that t1 will be x1 by vx and t2 will be x2 by vx. Am I audible? I just lost my internet.
Yes, sir, you are audible.
Okay, thank you for confirming. Okay, anyway, back to the problem. So we are calculating how much time will the electron take in regions where the electric field is there and in the region where there is no electric field. So we are calling those times as t1 and t2, right? So we want to know what are the values of t1 and t2. Note that we have already calculated the velocity of the electrons Vx, and x1 and x2 are given to us in the problems. So x1 is 0.1 meters and x2 is 0.45 meters. So just plugging in, this will be 0.1 and this will be 0.45 divided by 4.54 into 10 to the power 7 divided by 4.54 into 10 to the power 7. Okay. Now this comes out to be this will be 2.2 into 10 to the power minus 6 seconds. Minus 5 seconds, right? Because this will be 10 to the power minus 5, 10 to the power minus 7. Oops, okay, right. This will be 10 to the power minus 9 seconds. And this will be 9.9 into 10 to the power minus 9 seconds. Okay, great. Now we have T1 and T2 calculated. And now let us find out what next we want to find out is the value of this y1. So what is the deflection that the electron will feel when it is between these condenser plates? Okay, so we know that our acceleration or the force, that is mass times acceleration, that will be simply equals to charge times electric field. This will give us the acceleration as QE over M, right? And this E is nothing but QV by D, and then here we get N, because electric field is potential divided by the distance between the two plates. Okay, and then we can write this in terms of Q by M, and here V is 1500 and D is 0.03. Okay, So the acceleration comes out to be, this will be 3 10 to minus 2. Yeah, so this will be 5 0 0 0 0. Yeah, or 5 into 10 to the power 4. And here we have our q by m in multiplication, and this is meters per second squared. Okay, now we know a, what is the acceleration, we know the time t1 for which the particle is being accelerated, and what we want to know is the displacement y. We also know the initial velocity in y direction, that is 0. Okay, so in the figure here you can see that the particle is moving horizontally. There is no vertical velocity that the particle has here. So initial Vy, or let's call that Uy, that is 0. Okay. So now again, using the equation which we used earlier, S is equals to ut plus half at squared, what we will get is y1, which is our S, is, because this term is simply 0 because u is 0, this is nothing but half into a, which is q by m, times 5 into 10 to the power 4, and t squared, which we calculated here, 2.2 10 to the power minus 9, is this one, and we will square this. Okay, so we get y1 here in terms of q over n, and then if we find out the value, so this will be 2.2 squared times 5 divided by 2. This will be q by m, and then multiplied by 1.21. This will be 10 to the power minus 18 here, and this is 10 to the power 4, so 10 to the power minus 14, and this will be 10 to the power minus 13. This will be our y1. Correct? Why we need this y1? We need this y1 because if you draw a line here, to find out this total y2, your y2, because in this region there is no electric field, the particle just travels with a constant velocity, so your y2 will be vy times t2 plus y1, which is your v is equals to, sorry, your, this is y1 here, and this is your vy times t2. Now other thing that we need to calculate is vy, and for this we will use this equation, v is equals to u plus at, right? So here u is 0, so this term is again 0, and our at is nothing but q by m, 5 into 10 to the power 4 multiplied by 2.2 into 10 to the power minus 9. Okay, so this just gives q over m, 5 multiplied by 2.2, this is 11 into, or 1.1 into 10 to the power minus 4 meters per second. Now we have Vy and we have y1. So we can write y2 as y1 plus Vy t2. Okay. So this will be q over m 1.21 into 10 to the power minus 13 plus q over m 1.1 into 10 to the power minus 4 multiplied by t2. And where is our t2? Here it is, 9.9 into 10 to the power minus 9. 9.9 into 10 to the power minus 9. We can take q by m outside. Then we will get 1.21 into 10 to the power minus 13, and 9.9 multiplied by 1.1 will basically give us 10.89 into 10 to the power minus 13. Okay, and adding these two, we'll get q over m multiplied by 12.1 into 10 to the power minus 13. This is y2, and y2 is given to us here, 0.2 meters. So y2 is 0.2, and then we can just equate it to 0.2. So our q by m ratio will then be 0.2 divided by 12.1 into 10 to the power minus 13. Okay, so this will be 0.2 divided by 12.1 into 10 to the power 13. And this is nothing but 0.01653 into 10 to the power 13. And so finally what we get is, this becomes 1.653 into 10 to the power 11. Okay, so this is the value which we are getting. And finally, after a lot of calculations, we are able to find out the value of E by M. So I'll just summarize what we have done for this problem. So first of all, we had applied a magnetic field B, and by applying this field B, we are able to get rid of the deflection. So the deflection is reduced to 0 on application of magnetic field B. When that happens, we basically say that the net force is 0. The net force is 0. In that case, we can equate these two terms, one because of electric field, one because of magnetic field. And this gives us the velocity of electrons. And we are getting the velocity of electrons here. So we are getting the velocity of electrons as 4.54 times 10 to the power 7 meters per second. Now note that this velocity is pretty high, right? This goes into the relativistic region. But the calculations and the equations which we have used, we do not consider this thing as of now. If you really want to solve this problem properly, then the equations that we have to use are the equations concerning special theory of relativity. The answers that we are getting for the velocity, the q by m ratio, they will then get slightly modified. Okay, so that thing you can try on your own. Then what we want to find out is the value of E by M. And as discussed in the class, to find out the value of E by M, we first need to find out what is the displacement up till this point, what is the displacement y1, and what is the velocity vy of the particle when it reaches this point. Once you know that, you can then, using that values, you can easily calculate what will be the deflection y2 on the screen. Correct? Because the electric field is limited only in this region. Okay, this is the region where we have electric field, right? Only up till this point. So all the deflection that is happening is in this region. After this region, the particle just continues to move in a straight line. This is just a straight line. There are no more deflections. Okay, it is moving with a uniform velocity vy. This is a uniform velocity vy with which it is moving. It is moving in a straight line. The acceleration in this region is 0. So once we have the value of y1 and vy, we can then use those values as we have done to calculate the value of y2. And as you will note that this y2 will comes in terms of q by m here. You can note that the y2 is coming out in terms of q by m. Okay, here. Okay. And then once we have calculated what is our y2, and it is given to us that this value of y2, this is nothing but 0.2 meters. And then we can just plug in this value of y2 here and get the value of this q by m like this. So finally we can solve for q by m and then we get this value. Okay, any doubts in this problem? No? Okay, if there are no doubts, then I think we can end the session for today. It's 5 p.m. If you guys have any doubts, feel free to ask me in the forums. I will try to respond at least twice a week. And you can also send a email at this email ID if you want to discuss anything. So this is my name, Manav Beniwal at iisc.ac.in. Okay, if you guys do not have any doubts, then I think we can end the session here, and I'll see you next Saturday, same time, 3 to 5. If anyone has any doubts, they can ask, or I'll end the session. Thank you for attending the session, and thank you for the beautiful comments. Okay, I'll see you next Saturday then. Sir, I have left first 4 questions, so can I pursue it? Okay, it's fine if you have left the first 4 questions. That is fine. This video will be uploaded on YouTube. I will share the link. You will get the link in the Neptel website, and yeah. So the first 4 questions you can revisit there. Not an issue. Still, if you do not understand anything in the first 4 questions, feel free to ask in the forums, and I'll reply. I will also upload the PDF of this worksheet which we have done today collectively, the solutions and the problems which we have discussed today. I'll also upload a PDF, and the link will be provided to you on the website itself. Okay. Thank you so much for joining. This was really a wonderful session. I also learned quite a lot discussing all these things with you. Okay, I'll see you guys next Saturday. Have fun. Bye bye. I'll end the call.
Thank you, sir.
Yeah, you're welcome. Bye bye.